In this video, we are going to study about concept of moment of inertia. We know that inertia, it is nothing but the tendency of a body to remain in the state of rest or of uniform motion. That is, a position in change in existing state of the body. We also know that more the mass of the body, more is the inertia. In translational motion, mass of the body is a measure of inertia. But here we are going to study inertia in context with the rotational motion of the body. We know that ability of a force to produce rotational motion is called moment of force or torque. It means for producing rotational motion in a body, moment of force or torque is essential. We also know that a body at rest cannot start rotating about an axis on its own. This is nothing but inertia, that is a position offered by the body to the rotational motion. So we can say that a quantity that measures the inertia of rotational motion of the body is called rotational inertia or moment of inertia of the body. In order to discuss the concept of moment of inertia in more detail, we will derive an expression for kinetic energy of a rotating body. Now, in order to find kinetic energy of a rotating body, as you can see in this figure, we have considered a rigid body of mass capital M, rotating with a constant angular velocity omega about an axis passing through point O and perpendicular to its plane. But body is made up of n number of particles. So let m1, m2, mn are the masses of each particle situated at a perpendicular distance, say r1, r2, rn from the axis of rotation. Now let v1, v2, vn are the linear speeds of the particles of masses m1, m2, mn respectively. Now for finding the kinetic energy of the particle, we will consider a particle say of mass m1. Therefore for particle m1, its kinetic energy we can write say E1 is equal to half m1 v1 square. Similarly for particle of mass m2, its kinetic energy equation can be written as E2 is equal to half m2 v2 square. Similarly for nth particle, we can write this equation as En is equal to half mn, means mass of the nth particle, into vn square, means velocity square of the nth particle. But we know one relation, that is v is equal to r omega. Therefore we can write v1 is equal to r1 omega. For particle 2 with velocity v2, we can write v2 is equal to r2 omega for nth particle with velocity vn, we can write rn omega. Now we are going to substitute this value of v1, v2 and vn in their respective equations. Therefore we are going to get the kinetic energy of particle of mass m1, that is E1 is equal to half m1. In place of v1 we are going to substitute r1 omega. So we can add this nothing but r1 square omega square. Similarly for particle 2, we can write E2 is equal to half m2 r2 square omega square. And for nth particle we can write En. For nth particle, kinetic energy of nth particle is equal to half mn rn square omega square. Therefore for finding the total kinetic energy of this rotating body, we need to add all these kinetic energies of all these particles. So total kinetic energy of the rotating body, that is E is equal to E1 plus E2 plus plus En. Now we are going to substitute the values of E1, E2 dot 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 En in this equation. Here you can see half and omega square we can take out common, so we can write total kinetic energy of the rotating body E is equal to half omega square, which we can take out common into bracket. Here we can write m1 r1 square plus m2 r2 square plus dot 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 plus mn rn square. Therefore E is equal to half omega square into bracket summation I is equal to 1 to n mi ri square. Therefore we can write E is equal to half omega square into I. So this is the equation for kinetic energy of a rotating body, where this I is nothing but is this bracket term, where we can write this I, it is nothing but summation I is equal to 1 to n mi ri square. But we know that in case of translational motion, total kinetic energy is given by the equation E is equal to half mv square, where m represents mass of the body and v represents its linear velocity. Now if we compare both of these two equations, we can find the analogy between these. So this is the energy, total kinetic energy in rotational motion or of the rotating body, and this is the kinetic energy in case of translational motion, that is kinetic energy of a body in translational motion, that is ET. So these two are the energies of kinetic energy in rotational and in translational. So these are analogous with each other. Here half, here also we are having half. Here we have linear speed or linear velocity of the object, whereas here we have angular speed or angular velocity of the object. In this equation, m represents mass, that is m represents translational inertia of a body. Similarly, in this equation, the term I represents rotational inertia of the body, that is nothing but moment of inertia of the body. Therefore, moment of inertia of a rigid body about an axis of rotation is defined as the sum of product of mass of each particle and square of its perpendicular distance from axis of rotation. And mathematically, moment of inertia can be expressed like this: I is equal to summation I is equal to 1 to n mi ri square. Its SI unit can be written as SI unit m mass, so we can write this is nothing but kg. R it is the perpendicular distance of the particle from the axis of rotation, and its SI unit is meter, so r square, so we can write meter square. So SI unit of moment of inertia is kg meter square, and its dimensions can be written as m raised to 1 l raised to 2. For homogeneous rigid body, we can write this equation as I is equal to integral r square dm, where this dm is the mass of the small element and r it is the perpendicular distance of that element from the axis of rotation. From this equation, we can clearly see that moment of inertia of a body depends on mass, shape and size of the body, then distribution of mass of the body about given axis of rotation, as well as position and orientation of axis of rotation. Now we will discuss one example to understand how moment of inertia of a body depends on mass, shape and size of the body, as well as on the distribution of mass of the body about given axis of rotation and position and orientation of axis of rotation, for which we have considered a rod AB. In figure 1 and in figure 2, you can see we have considered a rod AB of the same length and both are of the same mass. But the difference between these two is, here you can see the axis of rotation is passing through its center of mass, whereas in this case the axis of rotation is passing through one end of the rod. Let I1 is the moment of inertia of this rod about an axis passing through its center of mass, and let I2 is the moment of inertia of this rod about an axis passing through its one end. In this figure we can clearly see that the distribution of mass of the body about given axis of rotation is very small, whereas in this case the distribution of mass about the given axis of rotation is larger, due to which moment of inertia in second case is going to be greater than moment of inertia of the first case. Therefore we can write moment of inertia, that is I2, is going to be greater than moment of inertia, that is I1. This is how we can understand if we change the orientation of axis of rotation, the moment of inertia will also change. As well as if you look at this formula of moment of inertia, we can clearly see that even though the mass of the object is going to be changed, then also the moment of inertia will also change.